Today we'll be talking about Lactobacillus plantarum and its interaction with Kalamata olives. So the domestication and cultivation of olives actually dates all the way back to 3500 BC in the area that's in between what is now known as Turkey and Syria. From there, the process spread throughout southern Europe and northern Africa, all around the Mediterranean Sea. Today, one of the oldest olive trees is in Palestine, and it is carbon dated between 3,000 and 5,000 years old. And today, the current top producing countries are all going to be around that Mediterranean region where olives originated. And since they have been domesticated, they have always carried very high cultural, economic, and symbolic value. So all olives contain a very bitter compound called oleuropein, and this just makes them too bitter to eat raw, so they have to be processed. One style of processing is the Greek or natural style, and that includes putting the olives inside of a sodium brine, which will leach out that bitter compound. And then it also uses the indigenous microbiota, and there are many, to facilitate lactic acid fermentation. And so today we're going to focus on Lactobacillus plantarum in that process. So Lactobacillus plantarum, the shape is in the name. It's rod-shaped. It's gram-positive, so it will have a thick peptidoglycan cell wall. It utilizes lactic acid fermentation for its metabolism, which means that it converts glucose into lactic acid. It is a facultative anaerobe, so it prefers oxygen-free or low oxygen conditions, which makes it ideal for fermenting foods. It's not halophilic, so it will prefer sodium concentrations between 3 and 5%, which is great for fermenting things like olives. So the metabolic process of lactic acid fermentation starts with glycolysis. And basically, it's a series of enzymatic reactions that will break down one glucose molecule into two pyruvate molecules. During that process, it will produce 2 ATP, which the bacteria will then use for energy. It also generates the coenzyme NADH, which is a molecule carrier, and it will carry high energy electrons and a proton, and in this case, it's hydrogen. Then the enzyme lactate dehydrogenase will catalyze the reduction of two pyruvates into lactic acid. And this is facilitated by the NADH, which is going to transfer the electrons and a proton that it's carrying onto the pyruvate molecules and turn it into lactic acid. NADH, when it does this, moves from its reduced state into its oxidized state, which is called NAD+. And then NAD plus will go back to becoming an electron carrier and can be used in that cycle, glycolysis cycle, once again to produce more ATP. The lactic acid that's produced as a result of this process will lower the pH level of the brine, and this is going to make it more acidic, which means that it will be more inhospitable to harmful bacteria, so they'll no longer be able to grow. And this is actually the preservation method that enables olives and other fermented foods to stay on your shelves or in your fridge. The high acidic content will also contribute to the brine of the flavor and the texture of the olive itself, and it's also going to degrade some of that bittering compound as well. So this will contribute to the overall flavor of the olive.